Hey guys, so this week, if you guys made it through the first couple of weeks, should be mostly reviews still, a lot of easy stuff for the most part, maybe some different ideas, but now we're going to take it to a whole new level. And I'm excited to to do this. Hold on, let's see. I'm excited that you got to this point, and we're really going to get into some of the things that really take you to that next level. So without any further ado, we're going to get started. So the first thing we're going to talk about this week is this idea of continuity. The idea of continuity is that something is continuous from point A to point B. If you can draw basically, if you can draw a path going from point A to point B without taking your finger off of your hand off of the page. All right. So, like for example, most piecewise functions, we think of them as piecewise because they're not continuous. So, like for example, this is a situation where it's not continuous. Okay. Now, it's not continuous everywhere, but it is continuous in some parts. So, like for example, let's say we had these points C and D. Well, between C and D, this function is continuous. So you can have something that's not continuous everywhere, but it is continuous at some places. That's the continuity in a nutshell. Obviously, when you have graphs and situations kind of like this, where you have some kind of like a vertical asymptote or something, obviously this function is not continuous everywhere, right? It's not continuous everywhere, but it's continuous most places, but not everywhere. And that's the whole idea of continuity in a nutshell. Okay, so after we talk about continuity, and I mean, it's a little bit more technical than that, but that's the main idea I want you to keep in your head. But after we determine continuity, if something is continuous or not, then we can talk about these things called tangent lines. So here's what happened. Basically, what a tangent line is it is a line. Let's draw a line here. Oops, that's not what I was trying to do. It is a line that touches this curve at one point, at only one point. All right, so tangent line touches curve at one point. All right, so the idea is, I could zoom in as close as I want to. This line is only going to touch this graph at one point. Okay, and that's it. Now, what is the significance of that? The significance of that is the fact that it only touches this at one point, and the slope at this point, so the slope of this tangent line, right, basically will tell you how your function is changing at that specific spot. All right, so the slope will tell you how your function is changing, or rather it'll tell you the rate of change of your function at that specific spot. So you can imagine that there are tons and I mean literally infinitesimally many of these tangent lines for most curves, right? Infinitely many of these tangent lines. Ooh, it's not it. Maybe we'll try to draw one like this up at the top. But there's infinitely many of these tangent lines, and every slope tells you a rate of change. So for example, if you look at, let's say, look at this tangent line here. All right. You can note that the slope here basically is 0. I didn't draw it very well, but you know, whenever you have a horizontal line, its slope is 0. Okay. And so since the tangent line slope, since the tangent line slope is 0, what we can say is that at this particular point, you can see that the function is neither increasing nor decreasing. So we can think about it like on this half of the graph, we can see the function is increasing, right? It's going up. But on this half of the graph, the function is decreasing, or it's going down. And at that particular point, where your tangent line is 0, the slope of the tangent line rather is 0, you can see it's neither increasing nor decreasing. Another thing we can do is tangent lines will tell us if we're increasing or decreasing. So like, for example, you can see quite clearly that there be, for this line, we'll call this line on, we'll call it line L. We can see that the tangent line, or the line L, has a positive slope. And note that the red function is increasing at that point. Whereas, say, this point right here, if we kind of drew a tangent line from there, we can see that it has a negative slope. And therefore, the function should be decreasing over here. At any point after our kind of like peak point. And so with all of this comes the big idea from this week, and that is derivatives. Okay. A derivative of your function, so the derivative in essence is just the rate of change of it could be either entire function or a specific piece of that function, specific part. Excuse my handwriting, but it is what it is. All right. So that's the idea of derivatives. Okay. So let's break it down. We're going to take this real slow. So suppose we have this curve. As a matter of fact, we're going to determine what the curve is. Let's say, let's do like 3x squared plus 2 or something. Okay, so we go up to 2, like that, and then kind of 3x squared. So kind of be something kind of like this. Okay. All right. Here's the idea. The idea is that is this. If, first of all, the first thing we need to know for us to have a derivative is the function continuous? Or at least, is it continuous on the between, say, points A and B? So like, for example, if we wanted to say at this point right here, Actually, we'll call this point C or something like that. At this point right here, and even if we could get a couple of points maybe in the neighborhood of C. So like, for example, let's say this point right here, which is A, and we'll say this right here is B. So we got B, C, A. Get rid of that. And what we can do is we can call this kind of like X1, X2, and so on. Actually, we don't even need this right here. So you got X1, X2, and then we can even think about this. And actually, let me redraw it real quick, actually, because I want to have even more space. So imagine we're just zooming into this thing here. So we just zoomed in. So this is A, this is B, this is point C, this is X1, and this is X2. Okay, actually, we don't even need C. Let's just say A and B. Nope, what I was trying to do. Yeah, I get to see me struggling here. Okay. And what we're trying to do is we're trying to figure out what is the rate of change from A to B. Okay. Well, basically, to find the rate of change from A to B is real simple. It's actually not hard. What you have to do first is you need to create what's called a secant line, or a secant line segment. And basically, a secant line segment is literally a line segment that will get you from A to B. So let's draw the curve a little differently so that you all can see that it's not the same thing. Then your secant line is here. So no, this is our secant line. All right, no, secant line is different than your tangent line. Tangent line hits at only one point. Secant line literally is the line between 2 points, okay, that are actually on your function or whatever. And so we're looking at the secant line. If I want to figure out what the rate of change of the secant line is, okay, then that's a real simple formula. You've learned it back in Algebra 1. We used rise over run, right? And the idea is with rise over run is that basically you have the change in y, so like y2 minus y1 over x2 minus x1. In other words, you have, you know, if we will, let's say this is basically, let's see. Let's say this is f of x1. And this point up here is f of x2. All right. So in essence, basically you got f of x2 minus f of x1 over x2 minus x1. And that is your rate of change between A and B, literally. Or let's say instead of, let's say that this distance between x1 and x2, let's say this distance is called h. Okay. So basically you can think about this as instead of x2, what we can say is basically this is going to be f, for example, of x plus h, because, or x1 plus h, if we will, because, you know, basically x1 plus h. Because basically you're starting with x1 and then you're just adding h, if you will. Remember, h is just that distance between the x's. That's all. Also, we could call h delta x sometimes. And this just means change in x. So remember, that's just the distance between x1 and x2. But they mean the same thing. H, change in x, delta x, they all mean the same thing. Now, here's where we learned about limits, and this is why it's important. Imagine that instead of point B being here, okay, imagine point B is right here. What does that do to H? Well, if B's getting closer to A, then H is shrinking. That means that the distance between A and B is shrinking. So if B, for example, is here, or B, for example, is here, and we created a secant line between A and B, let's say, as a matter of fact, instead of calling this B, maybe we'll call this B prime or something like that. You can see that the secant line between A and B prime is real close, right? They're really close. They're a lot closer together. And if we were to look at this H would be a lot smaller. And then what I want you to do is take that idea and imagine that B is getting really, 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 really close, infinitesimally close, to the point where H is not even existent. And when you finally get to that point, so, you know, I'll kind of try to visualize, show you visually what this kind of looks like. But basically, you imagine if A is right here and B is literally on top of A, pretty much. You can imagine you have a very tiny H, and your H basically is 0. If they're on top of each other, then your H is 0. The difference between A and B is 0 in terms of your X direction. And this is the idea. And once you actually hit it, once you actually get to the point where H is 0, then, and only then, do you have a tangent line. So your secant line has turned into a tangent line. And the idea, remember, behind tangent lines is that tangent lines will tell you the slope or the rate of change at that point. So what does this mean? Algebraically, what it means is that you can think about a derivative as the limit as x approaches, or rather, the limit as h approaches 0. In other words, your distance between A and B is getting really, 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 really small. And as h is getting smaller and smaller and smaller and smaller and smaller, you're going to find the rate of change. All right, rise over run. So once again, this is going to be x plus h, because remember, that is the distance of B, the y value of B. Go back. Here we go. And then minus f of x, basically distance of A, or the y value at point A. And then basically x plus h minus the x. Remember, that's a change in y's over a change in x's. It's literally your rise or run. Now, another way to state this is the fact that these x's basically cancel each other out, so you can get rid of them. And this is the formula for derivatives, or the limit formula for derivatives. So if you want to figure out the derivative of a function at any point, really at any spot, you can use this formula to do that. So, for example, let's take our 3x squared plus 2. All right. What I want to do is I want a formula so that I can just plug in any number and it will automatically give me the rate of change of the function anywhere. So I'll give you an example. Let's say, okay, I want to figure out the rate of change when x is 3. I want to figure out that rate of change specifically. Well, what I can do is I can basically say, okay, the limit as h approaches 0 of f of 3 plus h minus f of 3 over h. Okay, so there's a couple of things we need. First thing we need to figure out what f of 3 plus h is, which would be 3 times x, we know this is 3x squared plus 2 was the function. So we're going to do 3 times 3 plus h squared plus 2. Once again, just substituting for x, right? And you'll get, let's see, 3 times, 9 plus 6h plus h squared plus 2, which is equal to 18 plus 18h plus h squared plus 2. Okay, and then f of 3, which, by the way, is basically 20 18h plus h squared. All right, f of 3 itself should be a lot easier to figure out. 3 times 3 squared plus 2, which, let's see, is going to be, let's see, 27 plus 2. Which is 29. Make sure I did that. Oh, yep. Made a mistake back here. That's 27. All right, cool. I was about to say something's not adding up because I need some things to cancel eventually. All right, so let's go back. So we basically said the limit as h approaches 0 of f of x plus h, or 3 plus h in this case, f of 3 over h. Well, the good thing about it is 3 plus h is this, 29 plus 18h plus h squared. And then we did not plus, minus. So minus f of 3, which is minus 29 over h. And this is where I mean stuff needed to cancel. The 29s have to cancel, which is great. So you're left with just 18h plus h squared over h, which is the same thing as h times 18 plus h over h, and the h is canceled, and you're left with 18 plus h, which, remember, this is the limit as h approaches 0. So basically the h just goes to 0, and you're left with 18. Now, what is the tangent line to that point? Well, let's think about it. Tangent lines are basically, or any line can be written y minus y1. And this is just point slope form, m times x minus x1. And note, this is our rate of change, right? The derivative tells us our rate of change. So what we can do is we can say this is going to be y minus, y1 was 29. And let's see, 18x minus 3 is what we were plugging in. And so let's check it just to be sure. So we want Desmos here. All right, and we said 3x squared plus 2. And then the tangent line we said was going to be y minus 29 minus 29 equals 18x minus 2 or 3. And if you look at 3, you can see, okay, change this over here, but if we look at 3, let's make this 1, make this 1. Okay, or I guess maybe to make it wider then, let's change these, let's make this 30, it's negative 30. So it'll widen out a little bit, hopefully. But if once you get to 3:29, you can see that this line is definitely the tangent line because you can get infinitesimally close, and you can see that this line will never actually only touches the function. Yeah, it's hard to see, but basically this line will only touch the function at that one point, at this one point and this point only. So it's very helpful. And also the fact that the rate of change is positive tells you that its slope should be up. It should be going up, which makes sense. Now, what if, and I apologize for this being a long video, but what if you wanted to know what the, you wanted just a formula, so you could just plug in any number and find where the rate of change would be. And you can actually use it this way. So for example, we know our f of x was 3x squared plus 2, all right? Well, anyway, if I want to find the derivative of the entire thing, first of all, I have to ensure the fact that this thing is continuous. And yes, this is a polynomial function. It's continuous everywhere. So that's the first thing I need to determine. The second thing that I need to determine is the limit, as I keep writing x, as h approaches 0 of f of x plus h minus f of x all over h. Now, f of x plus h, just for reference, would literally be 3 times x plus h squared plus 2, which is basically the same thing as 3 times x squared plus 2xh plus h squared plus 2, but we'll hold on to that for a second. So basically, let's plug this in. So basically, we got the limit is h approaches 0 of 3x squared plus 6x h plus 3h squared plus 2. And the reason I'm getting that is I just basically just distributed this out. So don't be alarmed. That's all I did. Didn't do anything. 3h squared plus 2. Do anything super fancy. And then minus f of x. So minus 3x squared plus 2 and then all over h. Now, this might seem like it's a lot, but trust me, it's gonna be really nice real quick. So basically we got 3x squared, and I'm just rewriting the first part, h squared plus 2. But we can now distribute this negative out. And that should give us something good to see. Basically the fact that this part is can cancel with this part. And this is all over h. So once again, limit as h approaches 0. Now, what we can do is cancel, cancel, cancel. Oops, not that one. Cancel, cancel, cancel. And you're left with 6xh plus 3h squared all over h. Once again, it's the limit as x approaches 0. And so what we can do is we can factor h out. 6x 3h over h as x approaches 0. The h is canceled, and you're left with the limit as x approaches 0 of 6x plus 3h. Of course, as h is getting close to 0, that's just 0, which is equal to 6x. What is that? That is what is called f prime. F prime of x is the derivative of x. It's the notation we use for derivative of x. And what does this do? This tells you the formula to find the rate of change anywhere on your function. So, for example, so we know that f of x is 3x squared plus 2, and f prime of x, our derivative, is 6x. So let's say I wanted to figure out what the rate of change was for my function at a specific point. And let's say that I wanted to figure out at the specific point, -3. All right. Well, the good thing is I happen to know already what the actual point is, -329. But let's see if we can't figure out what the actually let's make it -1. Make things a little easier for ourselves. And -1, let's see, if we plug f of -1 in, there'll be the point -1. -1 squared is 1, so -1's 5, basically. Okay. So let's say we want to figure out, first of all, what is the rate of change at x equals -1, and then 2, what is the tangent line? What's the equation of the tangent line? Well, we don't have to go through everything we went through in the last one because we already know what the derivative of the entire function is. So all we got to do to find the rate of change is plug it in. F prime of -1 equals 6 times to -1, which is -6. And this makes sense because it's sloping downwards, right? It's sloping down. So you would expect that it would be also the derivative would be negative. Your rate of change would be negative at that point. So now what we're going to do is we're going to say, okay, find the tangent line. We know the equation for the tangent line is y minus y1. I keep writing y1 too much. And it's equal to m times x minus x1. And we already know our y1, x1 is -1, -5, because it's the point that we're looking at. So the tangent line should be y minus 5 equals m times x minus -1, but basically just +1. Oh, and our m at that spot was -6. Remember, your m will keep changing. Your rate of change depends on where you are in the function. All right, let's do it. Let's see if I'm right. All right. All right, we're gonna check this, but we're gonna go down here. And we're gonna type in our formula. So y minus 5 equals negative 6 x plus 1, and boom, you can see that's definitely your tangent line. And your slope is definitely sloping downwards. What about at 0? What about at 0? What if instead we want to look at 0 specifically? Well, if you think about it, your tangent line should be x equals 2, literally, right? Because that should be your tangent line, but let's check, make sure. So I'm gonna do this to the side over here, just real quick. F prime of 0 is gonna be 6 times 0, which is 0. And then we can say y minus, let's see, your y value is 2 equals m, which is 0, times x minus 0, because we plugged in 0. And so basically, you know, with y minus 2 equals 0, or y equals 2, which is indeed your tangent line. So derivatives are great. So this was kind of an overview. I don't know how long this took, but I hope you find it. I hope you guys found it helpful. And if you have any questions, just let me know.